on to scoping projects 1. So this is a scoping project update, and this will run for about the next half hour, and it's a series of videos of 4 different projects that have been funded over the last scoping project round. So these are scoping projects related to the Sustainable Production Theme 1. And there's a variety of STFC technology, facilities, and equipment on display within these themes. Some amazing videos there. So we have Neutron soil moisture probes for regenerative agriculture, hyperspectral infrared imaging for precision soil moisture mapping, predicting corn yield with UAV-based remote sensing, and then finally, feasibility studies on using Neutron and Raman spectroscopy to evaluate physical and chemical characteristics of novel green fertilizers. My apologies, the coffee has not kicked in yet this morning, but we have some amazing videos coming up there. Gareth, please hit the play button.
That I've been a part of. So there are 2 projects I'm going to present on today, but both of these fall under the umbrella of using STFC tech to better understand soil moisture dynamics. The first project I'm going to discuss is some recent efforts to develop low-cost neutron sensors for large area continuous moisture monitoring in partnership between a number of the northern universities. So in this project, we've been investigating the cosmic ray neutron sensing technique, which takes advantage of the fact that there is a constant flux of cosmic ray neutrons impacting the soil every second. Since neutrons have a high likelihood of interacting with hydrogen, it's possible to use the number of neutrons we detect above a soil to estimate the soil volumetric water content over large areas, up to 200 meters away from a single detector. Whilst this is a great match for field scale monitoring, existing neutron sensors are typically quite expensive and can be toxic. So our project has been looking at testing in the field an alternative low-cost neutron sensor design that myself and Lee Thompson came up with when I was at the University of Sheffield. In this project, we've brought together a number of STFC capabilities to produce in a short timescale 2 field-ready deployable prototypes. In partnership with the University of Durham and Sheffield's spin-out company, GeoOptic, support from the Food Network was used to assemble 2 neutron detector tubes based on low-cost scintillator technology, which emits light when a neutron interacts with it. These tubes were then characterized using a range of neutron sources by taking advantage of NPL's Measurement for Recovery program. After that, they were combined with a set of low-power Internet of Things data acquisition boards, which allowed us to produce a fully integrated neutron monitoring system, which could be deployed in the field and left to run by itself. With support from the University of Newcastle, these systems were deployed at Cockle Park Farm in June. One of these systems was deployed within 3 meters of an existing expensive neutron detector station, which is in use by the Centre for Ecology and Hydrology to monitor soil moisture on the site. Early comparisons are actually showing that there is a good correlation between our new lower cost system and CEH's existing system. And we're continuing to take data to try and understand this correlation over a long period of time. In addition, the other detector system was deployed at a neighbouring site, which is known to have a fast draining soils. And from this, we hope to evaluate the feasibility of using these systems to monitor soil drainage conditions for regenerative farming practices. Both of these systems are now scheduled to be left for around a year at Cockle Park to benchmark their sensitivity and confirm their stability under different environmental conditions. With the data they collect, we're now developing larger scale funding proposals to look at the feasibility of using distributed networks of low-cost sensors over a single site to better understand different soil moisture dynamics on different neighbouring fields. And just recently at the University of Durham, we also submitted a proposal to NERC to investigate whether these sensors could be used to support machine learning-based irrigation management in the future. In the second scoping project that the Food Network has supported, we've been investigating the use of a compact hyperspectral infrared imager to map soil moisture over a site. While satellite data can be used to understand variations in soil moisture over large areas, detailed satellite maps of soil moisture at the crop scale can be expensive. Drone-based mapping of crops offers an interesting solution to this problem, as control of flight parameters directly by the end user allows maps of a field to be built up with a truly customizable spatial resolution. This scoping project has been developing an integrated hyperspectral UAV platform focusing on the infrared reflectance range between 1000 and 1600 nanometers. Within this range, the reflectance spectra of soils are known to change significantly with increasing soil moisture. And recently at the Centre for Advanced Instrumentation at Durham, a compact hyperspectral imager has been developed that uses information from the entire shape of the soil's reflectance spectrum in this region of interest to estimate surface soil moisture. Compared to other photogrammetry techniques, the hyperspectral imager used in this project relies on push broom imaging to build up images of an object of interest. This is where individual one-dimensional slices are taken of an object, and the camera itself must be rotated or moved to build up a two-dimensional spatial image of the object of interest. The advantage of considering drone-based mapping for such systems is that when mounted to a moving aerial platform, the motion of a drone itself can be used to build up these images in real time. To support this, we've recently developed an open source workflow called MavBroom that enables direct interfaces between push broom hyperspectral images and autonomous drones, and it uses the widely available MavLink message protocol. These images here shown on the left-hand side are actually some of the stitched together images that are produced in almost real time obtained from the push broom imager. The majority of the Food Network scoping project support has been used to develop a robust UAV platform for this push broom technique. This system is based on earlier UAV platforms that were used by Anthony Brown in STFC projects to calibrate the response of Cherenkov telescope arrays. A particular focus has been spent on fully integrating the UAV avionics with the new hyperspectral imager, which enables a plug-and-play based system which has automated data pre-processing on board, and it allows us to add the camera when we need it to support other soil moisture mapping projects in the future. Final test flights are taking place of this system at Durham University now, and given that COVID restrictions are easing, we are planning on first test flights at Leeds University in the next few weeks, provided the weather is okay. What we hope to do at the University of Leeds is understand whether the infrared soil moisture maps we obtain can be used to optimize the placement of in-ground sensors and give a better representation of the entire field site soil moisture dynamics. Flying here in partnership with Leeds University will allow us to take advantage of an existing soil sensor network already deployed at the site. And it will also allow us to make comparisons with several additional sensors kindly donated to the project by our partner Dales LandNet, a manufacturer of low-cost soil moisture sensors here in the UK. Now that this capability has been established at the University of Durham, we are looking at alternative applications of this system for agriculture. And recently we submitted a secondary scoping project to look at the correlations between soil moisture and soil organic carbon within the infrared spectral region of interest. In addition, a secondary neutron sensor has been deployed at Leeds University, and we hope to actually bridge the outputs of both the scoping projects that I've presented here to better understand the footprint of these cosmic ray neutron sensors in varying soils using high-resolution infrared maps.
The fourth challenge for this research project is to come up with a yield prediction model for smallholders of sweet corn growers using UAV-based multispectral data analysis. Farms in Southeast Asia, as well as in many other parts of the world, are smallholders of just a few acres per plot. Due to the nature of sweet corn, once harvested, it has to be processed within 24 hours. No storage of any kind is possible. The ability to predict yield from these small-sized plots and to add them up together as a time series will not only allow the processing plants to optimize their operation, but to also help the growers to alleviate waste due to uncoordinated harvest. The methodology used in the study is twofold. One is to develop a software platform to be used by the Association of Growers to coordinate and orchestrate the planting and growing activities of their members. And secondly, to come up with an equation that utilizes the known vegetation indices as well as newly developed ones that affect yield, together with the actual measured yield of each of these experimental plots after harvest. A somewhat reverse engineering approach is hereby taken. The equation derived for yield prediction will then be used for the succeeding growing cycles. We hope to involve STFC's data scientists as well as to use the facility's computing resources. We also plan to expand this research to cover other types of corn cultivars, such as those used for animal feed, as well as those to be applied to corn silage cultivation to produce animal roughage feed for cattle, which is highly in demand but currently unknown in this region of the world.
Hi, I'm Ruben Sakrabani from Cranfield University, and the title of this feasibility study is using neutron and Raman spectroscopy to evaluate physical and chemical characteristics of novel green fertilizers. And I would like to acknowledge my co-investigators at STFC, Genevieve, Sarah, Hugh, and Jens. The focus of this project is looking at the food challenge, focusing on food security, in particular looking at the challenges related to sources of seeds and also fertilizers to ensure there's resilience in food production. Chemical fertilizers are important for food production, but they are energy intensive to produce. So in this project, we are looking at the feasibility of using a new technology by capturing CO2 into food waste and converting into fertilizer. And it's also very timely in terms of various policy drivers that we have, such as the net zero carbon, agricultural bill, the DEFRA 25-year plan, etc. And why this is timely as well, this feasibility study, is because we need to ensure there's traceability when using organic fertilizers, and that's where these novel approaches at STFC facilities comes in handy. So the two techniques that we're using at STFC are the Raman spectroscopy and specifically spatially offset Raman spectroscopy and neutron tomography. The neutron tomography is the figure which is shown by the cursor here, which focuses on giving information on porosity and structural composition, whereas the Raman spectroscopy is looking at near-infrared lasers to provide information related to chemical information in a non-invasive manner. And together, these two techniques will be able to provide the physical and chemical characteristics of this particular type of fertilizer to provide an estimate of traceability. So this is how the neutron tomography is set up. You can see that it's mounted in aluminum foil in front of the neutron imaging camera, and then it's bombarded with the neutron rays. And the next photograph shows the neutron radiography in terms of how the samples are stacked. And I'll show a short video next on how once the neutrons are bombarded on the pellets, how, if you imagine there are slicing that happens at each of these interventions within a pellet, as shown by the next slide, you can see the movie will give information about how the variation in the porosity occurs. So the movie is as follows. It's quite long, but I'm going to show you a shortened version of it. So you can see here, it shows the image as the slicing happens from the top to the bottom of the pellet. And you can see the pore space between the one particular pellet and the dense material is the more packed component, whereas the pore spaces are the ones that you can see. I'm going to slightly forward it So it gives you the slicing that happens as you go from the top end of the palette towards the bottom, and you can see as you go towards the base, the porosity changes considerably. So this gives an overview of the kind of the porosity and the physical composition of the palette. The next tool was the Raman spectroscopy, and this was providing the chemical composition. So we had some challenges in using these because of the low signal to noise ratio, and also due to the dark nature of the palette. So there was some absorbance was occurring, causing interference to the fluorescence. So we found that because of these very strong fluorescence, the intensity was compromised to some extent. So there was to be some kind of cleaning that has to be done in the spectra to get a much more clearer spectral for us in order to understand what are the chemical composition that's present. So it was a combination of using the transmission Raman spectroscopy and the spatially offset Raman spectroscopy. And here it shows some indicative presence of sulfate or ammonia or carbonate in the palettes that we analyze and their respective bands. So the Raman spectroscopy itself would not be feasible for this particular palette analysis, but can use in conjunction to get some complementary information. So we're hoping to carry this work forward by carrying out some further analysis using the same sample on both techniques, and hoping to write it up to short communication, and also use this as seed corn data to get apply for further funding from UKRI. And also we've been engaging very closely with the industry, and we have very successfully carried out a dissemination event at the Luton estate where the field trial is being carried out using the same fertilizer. And I was also interviewed in the BBC for Farming Today program on the role of green fertilizers. Thank you.
Wow, some amazing results from that series of scoping projects, and just seriously amazing and impressive things that have happened, you know, in such a short amount of time. And I think that's part of the amazing thing about the STFCN scoping model, being that, you know, we're providing small 8K grants, but show so much potential within this and can be built upon. As you saw in the first two of those projects, they were building upon previous scoping projects, which had gone off and done their own thing, but adapting tech and algorithms and other things to actually continue there. So brilliant work there. Please do put any questions in the chat for the investigators. They're online as well watching it, but congratulations to everybody in that first panel. That was just simply some amazing progress that's happened. And likewise, I know some of those people have submitted for the upcoming scoping projects as well, and will be excited to be seeing what happens in the scoping project calls there and what gets funded. So just some amazing things happening in that.